So, chapter 6. Oh, sorry, chapter 6. I'm still on chapter 6. I'm on 6 in my head. So, the title of the chapter is Advanced Pathfinding Techniques, Improving Performance and Quality. So what are the key chapter questions? Basically, building upon chapter 6. Chapter 7 deals with some common problems that you might have in pathfinding and how you might avoid them. So what are several causes of slow pathfinding? Where are you going to have hiccups in your code, and how can you avoid those? What techniques can be used to address these issues? What data structures can be used to quickly determine whether an agent can reach a particular destination? So is there anything you can pre-compute ahead of time that'll allow you to quickly know, like one computation, oh, I can or can't go, versus trying to search the entire environment to see if there's, one last path that might make it. What is the advantage of pathfinding a group of agents as a single operation? Is a series of short path searches more or less efficient than a single long path search? And what are two ways to take advantage of a simplified path network hierarchy? Okay, so pathfinding, performance optimization, failed pathfind operations. So in this example, right, you are running A star and you're at the point A, and obviously it's clear that you can get to point B because it's right next to you. But there's a couple different points that we kind of need to evaluate. So A and B are kind of in the same general location. C is a barrier, and D is on the other side of that barrier. So if we were to perform an A star search trying to go from A to D, there is no way that we could ever get to D. So we would try every single possible node that we could possibly get to, every single path, before failing out and finally saying, I guess I can't get there. And you never really know if you could have gotten there. Maybe there was an error computationally when you were trying to figure out the path. If you were trying to debug this would be really bad because it's only, you don't actually know if you ever had a failure. You only know that you didn't have a success. So how do we deal with this situation? So one is to have different zones. So you could basically come up with an algorithm that would traverse the entire node network and figure out which nodes are in the same zone. So obviously any barriers are going to be in their own zone. So that's zone 0. We can't do anything with it. It blocks us from getting anywhere. So what you could do is just kind of zip through, left to right, and just go back and forth. And, okay, I'm going to start off with this one being number 1. Okay, the adjacent node, I can get to that. That's number 1. Now I'm here, I can go here, and I can go there. I'm going to go down and right. All right, next one, keep going, across. Get to a barrier, start with a new number. All right, so on and so forth. Now you'll see if there's little cul-de-sacs like this, you're going to run into a problem where zone 3 and zone 1 are actually the same zone, right? But our algorithm just didn't know that because there was a barrier here. And so it started a new number. Like, it should have actually updated here if it could have, but it didn't, so now it's a number 3. And similarly here, because it wasn't updated here, because there was a barrier, it's a number 4. So whenever you come across a barrier, you would jump to a new number. And so that problem with the 3s and the 1s can be resolved. I'll just do it on the slide. So what you can do to resolve this is actually have another function that will go and compare the different zones. So in the process of going through these 3s, if I get to this point where I got a 3 from the one to the left, I'm now updating the one underneath me and the one to the right of me. Oh, the one to the right of me is a number 1 because it got updated in the previous row. I should make some sort of rule that says 3 is equal to 1 and then just deal with that. Not go back and reassign all the 3s to 1s because that's just a waste of an operation. Okay. So in addition to setting up these zones, you could figure out that different AI agents maybe can move in different zones because of their properties. So in this example, we have basically 2 pieces of land. Well, actually, there's 3 pieces of land. But, there's 3 zones that are land, number 1, number 3, and number 5. Maybe 3 and 5 is actually like an island that's one piece of land, but there's a barrier in between. And then there's 2 zones that are made out of water, 2 and 4. So we can imagine that there might be some AI unit that's only capable of traversing the land. So it would be able to move in zone 1, zone 3, or zone 5. But it wouldn't ever actually be able to go from 3 to 5 or 1 to 5. So you could limit, you could know instantaneously, oh, I'm going from 2 points in zone 5, I can do it. I'm trying to go from a point in zone 5 to zone 1, I can't do it. And similar, 1 to 3. You could also have a unit that maybe can traverse on water, so it would be able to move within 2 and within 4, but not between the 2. And then maybe you have a unit that's, amphibian. It can go between, it can go both on land and water, and then it can go everywhere. Because it can go here, it can go over the water, and then go to the land, and go over that water, and get there as well. Okay. That's a slide. That's an example. So, a problem you have in a very large level, this is going to deal with just wasted time in pathfinding again. So you're within the same zone, you can find a path. Now you're challenged with trying to find the optimal path in as short a time as possible. So once again, we're looking at A-star search over a long path. And in general, A-star search is about n squared in the number of comparisons it has to do, like order n squared. So based on the length of the path, it's roughly the square of that you're going to have to compare in path nodes. And so, as you can see, you're basically looking at a lot of different paths that aren't the optimal solution. You don't really need to compare anything over here. You don't really need to compare anything over here. We're intelligent. We know roughly, shortest distance is a straight line, so we're going to try and probably stay as close to a straight line as possible. We wouldn't really kind of veer off over here. A way around this, okay. A way around this would be to come up with a waypoint system. So you might mark several key points on the map, and rather than trying to pathfind from one spot on the map to another spot on the map, you would set up some key path nodes, key waypoints along the way that, I could move from A to waypoint 1 here, and then maybe there's another waypoint over here, and so I could traverse along these trying to move from my start to my finish. And this also kind of builds into the idea of the hierarchical path nodes that I'm going to go into in a little bit. But basically trying to abstract out a higher level path rather than trying to use every single node to kind of guide where you're going. Okay, group pathfinding. So some of the problems you have when you have multiple units all trying to move at once are the fact that, for one, they're all kind of in their own distinct locations. So, you'd like them to move together. How do you deal with that? One is trying to figure out kind of like their average starting point, and then trying to find a path from that to like some average finish point. So you have like, say, 4 units. They're in a regular square grid. So the average starting point is roughly in the center of it. And then you could pathfind from that point to the finish point. Obviously, you could have a problem where that might be inside a building. Then you could add a special case for that where you would just try and start from the unit that's closest to it. In addition, you also have different kinds of behavior that these AI units might want to use. So when they're all trying to go to the same destination, they're kind of gathering together, and they're going to want to move together. Versus if they're retreating away, it's kind of more important that they act quickly than they act intelligently. And then lastly, you have the problem where you may have units of different types trying to move together. So you may have like a tank along with infantry, soldiers. And so like maybe the tank can move faster than the soldiers. What do you do there? Do you let the tank go off on its own? Do you kind of group them together so that all the units move at the pace of the slowest unit? If you had like a plane and a tank, would they move together, or would the plane just go because it can get there faster and doesn't have the same encumbrances that